SwayamPrabha. Digital India. Educated India.
Good morning everyone. In the last module we have discussed on the gasification, and we have come to know that in a gasifier the syngas is produced and it exits from the gasifier at high temperature, say 600 to 500 to 600 degree centigrade temperature. So, that hot syngas it is cleaned. So, particulate the stage 1, then for other stage 2 or acid gas, then clean syngas for different applications. So, for different downstream applications we need to achieve certain quality of the syngas. It must be free from the all sort of impurities like acid gases etc., and it will be having certain H2 by CO ratio as per the requirement, except the electricity production. Electricity production does not need any requirement. So, once we will discuss on this utilization part or sections of this, we should concentrate first on the cooling and cleanup option. And another important point is that syngas here the typical composition CO is 40 to 60% say, and H2 it is a 20 to 30%, but here we need, so H2 by C this ratio is almost half, but we need somewhere H2 by CO ratio 2 or in somewhere all hydrogen, complete hydrogen. Therefore, we need to cool the syngas, we need to remove the impurities from it, as well as we need to control the H2 by CO ratio. So, all those things we have to do first, then we will go for different applications. So, in this module we will discuss on syngas utilization options, syngas cooling and conditioning, that includes acid gas removal and shift reactions. Shift reactions will increase the hydrogen concentration in the syngas and reduce CO concentration in the syngas. And then we will discuss on the processes for the production of some chemicals or some other utilities like say production of electricity etc. Here we can see that from syngas we can get hydrogen, we can get electricity, we can get SNG, we can get FT fuels, that is diesel, petrol and other FT fuels, and we can get methanol and many chemicals. Once we can get the methanol, that can be converted to DME, that can be converted to many other chemicals, as some of the chemicals are mentioned here like ethylene, propylene, polyolefin, oxochemicals, methyl acetate, acetic anhydride etc., all the some list are given here. So, we can utilize syngas in different routes. We will be discussing some important routes here like say electricity, SNG, hydrogen, FT and methanol synthesis and DME synthesis. So, we have come to know that we need to clean the syngas and cool the syngas. So, cooling can be done by direct quenching it or by indirect cooling. Any methods can be used. Direct quench helps to remove the particulates also. Once the syngas is cooled, then the part comes for cleanup. So, that for the cleanup means the removal of undesirable impurities. Obviously, the acid gases COS, H2S etc., there is no NOx in this case, it will be nitrogen because we have supplied controlled amount of oxygen. There will be no SOx also because we have supplied controlled amount of oxygen. So, if sulfur present in the feedstocks, it will be available in H2S. So, our major concern H2S, COS and CO2. So, these three are major concerns, we have to remove it, but if chlorine is present in case of your feedstocks, then that is another addition will be HCl or chloride. Now, this flow sheet says that at first the syngas, raw syngas containing different compositions and some other trace contaminants as mentioned here, the first step is hydrolysis of COS. So, COS will be converted to H2S by hydrolysis. It will give us H2S. So, plus CO2, H2S plus CO2. Then second step is to remove H2S and CO2 from the syngas, and that is acid gas removal unit. This acid gas removal unit gives us clean syngas gas as well as it H2S rich gas and CO2 rich gas. So, CO2 rich gas we can pressurize it and we can use as the source of carbon dioxide, or we can sequester it. There are number of methods for carbon dioxide sequestration, and for H2S gas which is enriched with H2S, that is used for sulfur recovery. There are number of methods for sulfur recovery, we will discuss now, and after recovering the sulfur from the H2S rich syngas, the tail gas is going for treatment. So, this is the acid gas treatment process, and for the removal of H2S and CO2 there are number of technologies available, and most of the commercial technologies are based on the absorption process, and the recent trend is to develop adsorption process or warm gasification. Now, if we see on the flow sheet, then it is clear to us this is 500 to 600 degree centigrade. Now, it is again say most of the cases say 250 to 300 degree centigrade is required. So, cooling, if we can treat this hot gas at warm condition, then it will be more economically feasible. But in conventional cleaning stages for H2S and CO2 separation, the conventional cleaning processes uses absorption based technology which are both chemical and physical absorption in nature. So, the temperature of the gas used in these systems either atmospheric temperature around 30 to 35 degree centigrade, or it may be below 0 degree centigrade up to minus 70 minus 60 degree centigrade is used. So, if we use conventional absorption process, so obviously we have to reduce the temperature here below atmospheric temperature, again we have to increase the temperature here to 250 to 300 degree centigrade say for particular application. So, once temperature down again it is increasing, so these thermal processes will reduce the overall efficiency of the process. But in place of this, if one process is available or can be developed which can separate H2S and CO2 at warm condition, that is warm clean process based on adsorption, that can be more economically feasible and attractive. But this is latest development and very few commercial plants are available on this technology. The most of the old commercial plants are based on the absorption technology, and there are basically three major absorbents has been reported and used commercially. Those are MDEA, that is methyl diethanolamine, Selexol, that is primarily dimethyl ethers of polyethylene glycol, and Rectisol, that is refrigerated methanol. So, this refrigerated methanol, Rectisol and Selexol, these two absorbents captures these H2S and CO2 by physical absorption, whereas MDEA captures these impurities from the syngas through chemical absorption. Due to this reason, the temperature for this MDEA process is around atmospheric temperature, whereas for these two Selexol and Rectisol the temperature is below 0 degree centigrade. So, obviously the cost is higher in case of Rectisol and Selexol process, but obviously there will be some advantage of this Rectisol process also. It will be giving more selectivity and more efficiency for separation. Now, we will compare these three syngas acid gas methods, that is MDEA, Selexol and Rectisol. So, MDEA, that is 30 to 35 degree centigrade, and temperature is say 30 to 35 and pressure is 2.94, that is around 30 bar, and it gives 98.99 percentage of 98 to 99% of H2S selectivity and removal. So, H2S removal is around 98 to 99% and CO2 removal is around less than equal to 30%. So, up to 30% CO2 removal is possible using this chemical absorption method, and this is developed by Union Carbide, UOP, Shell, Dow Chemicals, all those licensors are using this in their plant, and this is low capital cost. And Selexol process, this is also having temperature is less than 0, -4 to -7 degree centigrade, and pressure is also similar, say this is around 68 or around 68 bar, and then here H2S removal is again 99%, and carbon dioxide removal can vary. So, 99% H2S removal, carbon dioxide can vary. For Rectisol methods, this temperature is up to -60 degree, -35 to -60 degree centigrade. So, very low temperature. At this temperature the H2S capture capacity is very high for this absorbent, and CO2 is also captured almost completely. So, 99.5, this is having 99.5 to 99.9% H2S removal, and CO2 removal is also around 99%, 98.5%. So, 98.5%. So, on efficiency wise the Rectisol is the superior one. That is why in spite of higher cost the Rectisol has been used in commercial plant. MDEA has also been used in commercial plant because of its low cost, but Selexol is less used with comparison to these two. Here the technology licensors are given. The Rectisol is developed by Linde AG, and the important features we have discussed. Now, we will see the mechanism of syngas cleanup at hot conditions or warm cleanup of the syngas. At high temperature, if we use some metal oxides, then H2S is converted to that metal sulphide and steam. If we further increase the temperature, then the regeneration occurs. So, sulphide is converted to metal oxide again. So, for example, if we use ZNO plus H2S, then it will give us ZNS plus H2O at high temperature, that is around say 500, 315 to 530. So, 315 to 530 degree centigrade. So, this reaction takes place. Further ZNS is heated and then it gives us, this is heat, it gives us in presence of oxygen ZNO plus SO2, ZNO plus SO2. This temperature is 590 to 680, 590 to 680 degree centigrade. Now, once SO2 is produced, which is coming out from the adsorbed materials. So, that will be having high concentration of SO2. So, that SO2 can be used for further applications. Like say SO2 can be used directly for the production of sulfuric acid, because SO2 will be converted to SO3 by vanadium pentoxide B2O5, then it will give SO3 to concentrated H2SO4, it will give oleum, feed dilution, it will give concentrated H2SO4. So, that way we can get sulfuric acid from this, or we can recover sulfur directly, that is the reaction is like this: SO2 we have, that will be reacting with hydrogen and it will give us 1 by N SN, that is elemental sulfur and H2O, or this SO2 can react with CO, and it can gives us 1 by N SN plus CO2. So, that way directly we can recover the sulfur, or Claude process is also there for the sulfur recovery. For solvent for absorption method also, using Rectisol, Selexol or MDEA, when it is regenerated, the or desorption proceeds, then the H2S comes out. So, that H2S can further be used for sulfur recovery through Claude process. Now, we will see the reactions involved in Claude process. In this Claude process, H2S partially reacts with oxygen and forms SO2 and H2O. Then SO2 and H2S, this reacts in presence of some catalyst Fe2O3 or Al2O3, and it gives us 3 by 8 S8 plus 2H2O. This is, or H2S can also react with oxygen and directly it can gives 3 by 8 S8 plus 3H2O. So, this elemental sulfur is generated and that can be produced, can be processed for different production. Okay. Now, we will concentrate on the conditioning part, that means how to increase the hydrogen concentrations in the syngas and reduce CO concentration in the syngas. For this, shift reaction is carried into the shift reactor. So, shift reactor we see it can be placed here before acid gas removal, or it can be placed after acid gas removal. So, this syngas conditioning or shift gas reactors can be placed before or after the acid gas removal. If we place in different positions, then we will be having different phenomena, particularly here the temperature is higher, temperature is lower, because the syngas after cleaning the temperature will be lower, but these shift reactors will be having or requiring certain temperature. This shift reactor will also be requiring certain temperature. So, when we will be using after switch shift reactor and source shift reactor before this acid gas removal, this will be having different efficiency, and as here the syngas is containing more impurities, the catalyst will also be different. So, now we have got two types of shift reactions or reactors. So, one is your high temperature shift reaction, another is low temperature shift reaction. So, shift reaction temperature may be of high temperature and low temperature. So, high temperature means say 320 to 450 degree centigrade, and low temperature means say 200 to 250 degree centigrade. So, these two reactors, under these two conditions, two different catalysts have been used. So, the high temperature catalyst is basically Fe2O3, Cr2O3, and in this case low temperature, that is your Cu, ZNO, Al2O3. So, these are two catalyst has been used. Now, development in the catalyst section, catalyst side has given another catalyst which can be used for a wider range, that is cobalt molybdenum Al2O3 catalyst. Now, if we think about these two catalysts, there are some differences. This Fe2O3, Cr2O3, this catalyst typically has a relatively less selectivity, that Cu, ZNO, Al2O3 has higher selectivity for hydrogen productions. However, this has lower resistance to sulfur and chloride impurities. Now, to achieve the conditioning of the syngas, we may use the sweet shift reactions or we may use sour shift reactions, but whatever reactions we use, we need to follow both high temperature and low temperature shift reactions. In case of sweet shift reaction, typical two high temperature shift reactors and one low temperature shift reactors are used, and this say 44% of CO can be reduced to around 2% or 1%, around say 2% or 1 to 2% by two high temperature shift reaction. And when we want to get less than 1% of CO, then another LTS is required. So, we can get up to around 44% to 0.5%. The similar thing we can get here using sour shift reactions also, but in this case more steam is required. So, the catalyst which is used in case of sweet shift reactor, that are more costly but high efficiency. So, reactor volume is less in this case, but for sour shift reaction the catalyst are less cheaper relatively, but it the reactor size is bigger. So, bigger reactor size. So, this is the difference between the sweet shift and sour shift reactor. Here some typical example is given how the quality of the syngas changes after shift gas reactions. So, the basic reactions is CO plus H2O, it will give your H2 plus CO2. So, this is the basic reaction. Now, in this reaction hydrogen is increasing. So, here hydrogen you see hydrogen is increasing from 43.01 to 61.53 and CO is reducing 49.98 to 1.18. CO2 is also increasing because CO2 is increasing, but H2O we are not getting much change, because we also need some additional steam, but here it is not changing, because when the syngas is taken for the analysis, then that during analysis temperature reduced and H2 is condensed, that is why this value is not changing much. Now, we will discuss on Fischer-Tropsch synthesis. So, in case of Fischer-Tropsch synthesis, CO and H2 containing syngas, the ratio having H2 by CO is equal to 2. So, this syngas is reacted in a FT reactor where syngas is converted to wax, and that wax is further processed through hydrocracker and then it is after distillation we get different fractions naphtha, kerosene, distillates, and the lower part of it, the waxy raffinate, it is recycled for hydrocracker. And the light fractions which is generated in FT reactors, that goes and after condensation it gives light wax and light oil, which is processed with this wax part through the hydrocracker to produce the lighter fractions, which is fractionated in distillation column. So, this is the flow sheet of the Fischer-Tropsch synthesis, and this reactor part play a significant role. The basic reactions which take place in this are CO plus 2H2, that gives us CH2N. So, we get paraffin and we get olefins, basically the paraffins are wax. So, NCO plus 2N plus 1 H2 will give us CnH2n plus 2 plus NH2O. This is for paraffins, and NCO will react with 2NH2 and it will give us NCnH2n plus NH2O. So, this is your olefin and this is your paraffin. And shift reactions also takes place in this reactor. So, the Fischer-Tropsch synthesis, the reactor temperature may be high and low. So, high temperature means 325 to 370 degree centigrade, low temperature means 220 to 270 degree centigrade, and the catalyst either may be Fe based, iron based or cobalt based. So, iron based catalyst is fuel flexibility is there, and cobalt based catalyst is not so flexible with fuel, but it is better to use syngas with high H2CO ratio, and it is basically used for the syngas produced from natural gas. And ZSM5 supported bimetallic FT catalyst has also been developed in later stage. In this case, the gas hourly space velocity is maintained around 700 per hour and pressure is 15 to 30 bar. Under these conditions, only the variations of the high temperature and low temperature, the product distribution will change. So, you see here the C plus for high temperature, the C plus fractions is 50 to 8%, whether the wax fraction is less, only 4%, but it is low temperature FT synthesis, we will get higher wax, that is equal to 50% around, and we will get C plus fractions less, 20 to 30%, and the gasoline will be more in case of high temperature FT synthesis reactors, that is 2:1 gasoline is to diesel ratio, and when the low temperature is used, the gasoline is to diesel ratio is 1:2, and Seaton number also varies in these two cases. Next we will see some applications of this gas, syngas into different purposes. So, Sasol plant at South Africa, natural gas based plant, it is in 1990 it is established, and for all these are for FT synthesis. So, another is Mosgas plant South Africa, Bintulu plant Malaysia, GTL plant at Australia, Pearl GTL project Qatar, and Sannijaru refinery Italy. So, here one interesting information we get that all the plants are having very large capacity. So, 12,000 barrel per day, 10,000 barrel per day, 1,40,000 barrel per day, but these technology will not be suitable for the case of the biomass and waste gasification. The syngas which is produced from biomass and waste, the capacity is not much, the plant capacity is less, but here the plant capacity is very bigger. So, biomass and waste gasification and corresponding utilization of syngas to FT synthesis will be feasible only when we will be getting more compact reactors with higher efficiency and heat transfer, and efforts are going on, and in near future we will get more compact reactors and the scenario will be changed and biomass the syngas from biomass and waste will also be suitable for FT synthesis. So, up to this in this module, thank you very much for your patience.